Okay, welcome to your video lecture on section 10.1, two-point boundary value problems. In many important physical problems, there are two or more independent variables, usually space and time. Thus, the corresponding mathematical models involve partial differential equations instead of ordinary differential equations. Partial differential equations are differential equations where partial derivatives are involved. In this chapter, we will solve some special partial differential equations using the method of separation of variables. The outcome of the separation of variables process is the necessity to solve a boundary value problem, which in this case is an ordinary differential equation where the independent variable is actually the spatial variable x. These boundary value problems are similar in many ways to initial value problems, but have some substantial differences as well. So many physical applications often lead to a problem in which the value of the solution y of the differential equation is specified at two different points. So remember, for initial value problems, we have y and y prime specified at the same point. Here, what we're going to have is a very similar looking differential equation, but our conditions are actually what are called boundary conditions. So we're going to actually specify what the value of the function is at 2 points alpha and beta on an interval. Okay. The variable x is usually the spatial variable, so we consider this sort of number line to be denoting where we are in space. Okay. To solve a boundary value problem, what you need to do is solve the differential equation, so find a general solution. That'll be very similar to what we did for initial value problems, but then what you need to do is actually make sure that the differential equation satisfies both boundary conditions, which can often be difficult. Okay, while boundary value problems can also be posed for nonlinear problems, we will consider only the linear case in this course. A little bit of terminology here. The right-hand side, g, if that g is 0 and the boundary conditions are also 0, we say that the boundary value problem is homogeneous. Otherwise, we say it's non-homogeneous. So, for example, if we have this differential equation here, y double prime plus 4y is equal to 0, with y at 0 being 0 and y at 1 also being 0, that's homogeneous. But if the right-hand side is sine of 3t and say y of 0 is 1, then we have a non-homogeneous problem on our hands. Okay. Although initial and boundary value problems appear to be similar, it's more of a superficial similarity. For example, the mild conditions on the coefficients p, q, and g for initial value problems guarantee not only the existence of a solution, but also the uniqueness of a solution, at least in a given interval. For boundary value problems, actually what we have is a structure similar to that of linear equations seen in 309. So for example, if you remember from 309, a linear system of equations, ax is equal to b, can either have 0, 1, or infinitely many solutions, and that of course depended upon whether the matrix A in the square case was invertible or not, right? And corresponding systems of homogeneous equations, ax is equal to 0. Remember, x equals 0 is always a solution, the trivial solution, but you could also have infinitely many solutions as well for those problems. And so what we're going to see in these boundary value problems is a very similar structure. So for example, if we look at this boundary value problem, this homogeneous boundary value problem, y double prime plus 9y is equal to 0, with y at 0 and pi over 2 both being 0, what we have is this general solution, c1 cosine of 3x, c2 sine of 3x. If we plug in the first boundary condition, this will mean that 0 needs to be c1 times cosine of 0, which is 1, plus, and then sine of 0 is 0. This means that c1 needs to be 0. If we plug in the second boundary condition, what we'll see is that 0 needs to be equal to, and we already know c1 is 0, and then plus c2 times sine of 3 pi over 2, which is negative 1, implies that c2 also needs to be 0, which means that our only solution is the trivial solution, y is equal to 0. Okay, so this homogeneous boundary value problem had just the 0 solution. On the other hand, if we consider this non-homogeneous problem where we have a right-hand side of cosine of 2x and a boundary value that's non-zero, we again get the general solution of the homogeneous equation, but we also get a particular solution, which this was found via the method of undetermined coefficients, cosine of 2x over 5. If we look at what the boundary conditions force us to have, what we'll see is that 0 needs to be equal to C1 plus a fifth, okay? And the second boundary condition tells us that 1 needs to be equal to minus C2 minus a fifth. And we can solve both of those, right? This would mean that C1 needs to be negative a fifth and C2 negative 6/5. What we'll have is a unique solution to this non-homogeneous problem. Y is equal to minus cosine of 3x over 5 minus 6 sine of 3x over 5 plus the particular solution cosine of 2x over 5. So here what we see is what we saw in linear algebra, where the homogeneous problem had just the trivial solution and the non-homogeneous problem had a unique solution. On the other hand, if we look at another example, a homogeneous boundary value problem, the same exact differential equation, but instead of having y at pi over 2b 0, we assume that y of pi is equal to 0. Again, we have the same general solution. We have the same conclusion about C1 because it came from the first unaltered boundary condition, but this second boundary condition stated that 0 needed to be equal to C1 cosine of 3x, which is 0, plus C2, and then sine of 3 pi. Sine of 3 pi is already 0, which means that this equation is just redundant. 0 is equal to 0. So what we'll have actually is that y can be any constant multiple of sine of 3x. And so what we have there is infinitely many solutions to the homogeneous problem. And if we go up to the non-homogeneous case, again, where we have the right-hand side as cosine of 2x, and the second boundary condition being y of pi is equal to 1, what we'll end up with is a system of equations that imply that C1 is both negative a fifth and C1 is minus 4/5 at the same time. Of course, this is impossible. And so the homogeneous problem had infinitely many solutions, but the non-homogeneous problem actually had 0 solutions. Okay, so what we're seeing is sort of all of the different cases here. Okay, thank you.